Hi everyone, and welcome to this hand-on course from EasyEDA. Previously, we completed the hardware design part of the project, and now we're officially stepping into the software development phase. This is lesson 1, and today we're going to talk about how to set up the development environment and what the development workflow looks like. So in this lesson, we mainly focus on writing control programs for 180-degree servo motors. Now, you might ask, why do we recommend 180-degree servos? Let's compare them and you will see. The 360-degree servo, to be honest, is more like a continuously rotating motor. Sure, it can spin all the way around without stopping, but here's the thing. It can't accurately stop at a specific angle. You can't just say rotate to 90 degrees and expect to do that. If you want precise control, you'll need a calibration setup and manually fine-tune it, which is pretty tedious. But with the 180-degree servo, it's a whole different story. It comes with an internal angle sensor. That means you can control it very intuitively. If you tell it to rotate to 90 degrees, it will rotate exactly to 90. If you try to turn it beyond 180 degrees, it simply stops. In fact, forcing it might even break it. There's also a difference on how they are controlled. 180-degree servo uses PWM to control the rotation angle. 360-degree servo uses PWM to control the rotation speed. So the control code is totally different. You can't use the same program for both. You can also tell them apart by just looking at them. If there's an angle sensor and a mechanical stop on the right side of the servo, it's a 180-degree one. If it's just empty, it's more likely a 360-degree servo. So if you're a beginner, I strongly recommend going with the 180-degree servo. It's much easier to work with and you will see results more clearly. For this project, we'll be using VS Code and Platform IO for all our software development. You're probably already familiar with VS Code. It's one of the most popular code editors out there. It runs on Windows, Mac, and Linux, has tons of plugins, and a super active community. If you ever run into a problem, chances are someone's already solved it. Platform IO, on the other hand, is a development framework specifically designed for ARM systems. It integrates very well with the VS Code, and best of all, it's free and open source. Platform IO supports a massive range of chips: ESP32, STM32, GD32, Raspberry Pi, ESP8266, you may name it. Basically, all the mainstream chips are covered. And it's really lightweight. For example, if you only work with ESP8266, it only downloads what you need. Doesn't waste space installing 50 gigabytes worth of stuff you'll never use, unlike some other IDEs. One of its biggest strengths is the clear project structure. Your source files, headers, libraries, and config files are all neatly organized. Even beginners can figure out that what's by just looking. Of course, you don't have to use VS Code. Platform IO supports other editors like Vim, Visual Studio, and Qt Creator. But VS Code is the most convenient choice for most people. Let's go step by step, starting from scratch. You can download it from the official VS Code website, or just search for VS Code in the Microsoft Store on Windows. Click and install, super easy. This is super important. Platform IO relies on Python in the background to handle dependencies and tool chains, so you must install Python first. Go to the official Python website and download it. Make sure you check the box that says Add Python to Path during installation. If you skip that, Platform IO won't be able to find it. On Windows, you can also install Python directly from the Microsoft Store. I recommend using versions between 3.9 and 3.12. If it's too new, it might not be compatible yet. Open VS Code go to the Extensions tab, the little square icon on the left, and search for Platform.io IDE. Click Install. After installation, the first time you open it, Platform.io will download some packages from the internet. It might take a few minutes, so just be patient. Once everything's installed, let's create a new project. In VS Code, click the Platform.io icon to New Project. Give it a name like EasyEDA. Set the board to Node MCU 1.0, which is ESP8266, and choose Arduino as this framework. You can use the default folder path or customize it if you want. Click Create and let it finish initializing the workspace. Now let's walk through the Platform.io project structure. PIO folder. This is where the build files go, like the compiled bin files. You can flash these directly onto your board without compiling every time. LIB folder. If you've imported third-party libraries, their source code goes here. You can edit them directly if you want to tweak the behavior. Include folder. This is for header files. Keep things clean and organized. Another lib folder inside. This one's for your own custom library files. SRC folder. This is the main source code directory. This is where you write your actual code. Platform.io supports both C and C++. Don't worry if you don't know C++. It's backward compatible with C, so you can totally write everything in C if you prefer. There's also a test folder, but we won't use this in the project. The .gig ignore files tells Git which files to ignore. Again, not something we'll worry about here. And finally, there's a platformio.ini file. This file is super important. It defines the compiler settings, environment, MCU type, partition schemes, and so on. For example, ESP8266 typically comes with the 4 MB of flash. By default, 2 MB is used for code and the other 2 MB is reserved for OTA, over-the-air updates. If your program is too big, you can customize the partition table and specify a new on right here in platformio.ini. So what's the thinking behind this setup? Why did we pick ESP8266? 3 main reasons: enough GPIOs to control servos, read buttons, and drive the OLED screen. Built-in Wi-Fi, so no need for an extra module to get online. Can be controlled directly through a web page, super convenient. We're using a web-based control for this. The control panel is just a web server page that you can open for your phone, PC, or even an old school browser phone. Buttons are optional. You don't have to solder them on. You can also expand to other input types later. We'll cover expansions in later lessons. We'll use PWM to control for servo motors, adjusting their angles based on the high-level time of signal. For communication, we use HTTP APIs and WebSocket for real-time commands. This includes sending facial expressions to the screen or movement commands to the servos. ESP8266 makes everything so much easier, especially compared to developing native apps across platforms. Now that we've covered development strategy, now let's talk about which GPIO we are using. The OLED screen connects over I2C by default, SDA is GPIO 4, SCL is GPIO 5. These defaults are defined in the SDK and usually don't need to be changed. Of course, if needed, you can change them via software. It's flexible. For PWM servo control, we will use GPIO 12, 13, 14, and 16. For button input, we'll use GPIO 2 and GPIO 15. These are customizable, but if you're a beginner, it's best to stick with the default layout we provide. Alright, to wrap up this lesson, here's what we covered. How to choose your environment, why we choose VS Code and Platform IO, cross-platform, open source, strong community, how to install everything, installing Platform IO, creating a project, and setting up the development tools. How the project structure works, a breakdown of every file and folder in your Platform IO project, and the basic development flow. Why we picked ESP8266, which GPIOs we were using, and how the software architecture works. That's it for this lesson. Thank you so much for watching, and I'll see you in the next one.